Okay, so we're on to the next part of our project 4. And so I clicked on the second tab, Triangles in the Real World, Part 1. Question 1. In pinhole geometry, similar triangles are created between the original object and its image because the light entering the opening reflects the image of the original object on the wall. Use the following information and the image to prove why the two triangles are similar. Alright, so we're given segment AB is parallel to segment DE. And I want to also discuss this image. So segment AB is parallel to segment DE. The other thing I know about this is that we have vertical angles right here. And because they are vertical angles, they have equal measures. So they would both be 30 degrees, and because they have equal measures, they would be congruent. The other thing I want to expand is that AB is parallel, very parallel, to DE. So this line, B to D, would create a transversal, and in those transversal angles right here, where it's intersected, we would have the alternate interior, alternate exterior, the same side interior. Those theorems are included in that. And if you were to look at this diagonal, it also creates a transversal between two parallel lines, and the angles right here would be, we would have alternate interior, alternate exterior, and we can use those lists of postulates. So let's, with that information tucked away in the back of our head, let's look through this proof and see which direction they were taking it. So segment AB is parallel to segment DE. That is given. Angle ABC is congruent to angle EDC. Alternate interior angles. So what angle did they talk about there? They were talking about line AB and line DE, and they were talking about angle ABC. So they were talking about this transversal, B to D, being a transversal. Alright, so they were talking about angle ABC, so A to B to C. They're talking about this angle formed here is congruent to angle EDC, so the vertex is right here. And they are alternate interior angles. How I think about this is these two parallel lines are sides of a rectangle, and if I were to just picture that this was enclosed, are these angles inside the rectangle or are they on the outside of the rectangle? And since they fall inside, the next question that I ask are they on the same side, like on the bottom, or are they on the top? And since one's on the top and one's on the bottom, they're alternate interior angles. So that's how they came to that conclusion. And now they're talking about angle ACB. So if we look at angle ACB, this is the angle we talked about knowing in the beginning, is congruent to angle ECD. So E to C to D. The vertex is at C. And so what is the reason for that? And that is because they are vertical angles, and vertical angles have the same measure, therefore we can say that they are congruent. So by the vertical angle theorem, that is why those two are congruent. And then since we have two angles that are congruent with their corresponding angles in another triangle, we can say that they are similar. For question 2, on a city's map, you can discover some similar triangles created between the places point A, B, C, D, and E as shown in the following figure. Two lines cross at point A, and there are parallel segments BC and DE connecting the two lines. Point B is between points A and D, and point C lies between points A and E. Use the following information and the image to prove why the two triangles are similar. So we are given that AB is equal to the length of it. So this is the length of AB is equal to 2. So this length right here is 2. The length of BD is 3. The length from A to C is 5. The length from C to E is 7.5. And the length of BC is 4. And the length of DE right here is 10. Okay, so now we have to prove triangle ABC. I'm going to highlight that. ABC, this triangle right here. We need to prove that it is similar to triangle ADE, to the larger triangle, which I'm going to use ADE to this triangle right here. So if I were to draw these two triangles separately, we would have ABC, ABC, which is 2, 4, 5, and we would have triangle ADE. So ADE, which, if we want to find the length, we would add the two segments together. So 2 plus 3 is 5. So AD's total length is 5. D to E was given as 10. And A to E, we would add these two together, so it would be 12.5. So that's the information we can gather from the diagram and the given information. Because these two triangles we need to prove that are similar. So in this statement, it's stating length AB equals 2, length BD equals 3, length AC equals 5, length CE equals 7.5, length BC equals 4, length DE equals 10. Reason is it's given. Then it's saying that the length of AD is equal to the length of AB plus the length of BD, which we did. The length of AB and BD is equal to the total length. And that's how we found out that it was 5. And they're also saying that AE's total length is equal to AC, the length of AC and the length of CE. And that's what we did. We added them together, 5 and 7.5, to result in 12.5. And the reason we can do that is by segment addition postulate. And then they substituted the lengths in and simplified. And now they're talking about ratios of corresponding sides. So they took AB, corresponding side is AD, so 2 divided by 5. The other corresponding sides ratio was AC, which was 5, and AE, which is 12.5, which reduces down to 2 over 5. And the other corresponding side is B to C, and D to E. So the ratios of the corresponding sides are all of the same, which is what this is stating. The transitive property, since AB over AD equaled 2.5, and 2.5 equaled AC over AE, we can state that those two are equal. So they're just cutting out the 2.5. The transitive property is skipping the 2 over 5 fraction. And then now it states triangle ABC is similar to triangle ADE. What is the reason? Well, what did they use? They just showed that all of the ratios of the corresponding sides were equal to each other here in statement 5. So we have the side similarity theorem. We were talking about all of the sides. Angle is talking about two angles. This did not talk about any angles. So that is why we can use our proof to help us. It was talking about the sides. So now, similar triangles are also used in indirect measurement. For example, in the following figure, to measure the distance across the lake, a surveyor located the points A, B, C, D, and E as shown. Two lines, segment AE and segment AD, intersect at point A. Point C is between points A and E, and point B is between points A and D. Use the following information in the image to prove why the two triangles are similar. So, we're trying to prove that ABC is similar to triangle ADE. So I'm going to draw them again separately. So ACB is the yellow one. So if we have this little yellow triangle, this is A, B, C. And then triangle ADE is this much larger triangle, ADE. It's that whole area right there, and so I'm going to draw that one. And this point was A, B, C, and use the given information. Alright, A to B is 12. So A to B is 12. That's 12. A to D, this total length, is 16. So our total length, A to D, was 16. A to C is 9. So A to C is equal to 9. And A to E, the total length, is equal to 12. So here's an indirect measure. Since I know A to B is 12 and I know the total length is 16, that means B to D has to be 4. And similar indirect information, we know A to C is 9 and the total length is 12, so that means C to E has to equal 3. That's just information that we know. And also notice that these two triangles overlap on vertex A. They both contain the same angle, vertex A. So this angle and this angle are the same. So that's information we need to know. Alright, so now statements, they restated the side lengths for each triangle because it was given. Ratio of corresponding sides. The corresponding sides, AB, corresponding side is AD. And how would I know that without it being given? In the triangle, it tells you which order to go in the vertex. So this is the first vertex, the second vertex, the third vertex to go to. First, second, third. And since A to B is from your first vertex to the second vertex, it lists, and A to D in the other triangle is the first vertex to the second vertex it lists. Those are corresponding sides. And same for AC is corresponding. It's the first vertex to the third vertex, and A to E, first vertex to the third vertex listed in its title. So those are corresponding sides, and that's how I know. The ratios are the same. And then, since they both equaled 3/4, they use the transitive property of equality. Angle A is congruent to angle A. Definition of congruent angles. I might have a problem with that one. Let's see if it gives it. And then triangle ABC is congruent to triangle ADE. Side angle side similarity theorem. All right, what change, if any, should be made to the reason for statement 4? Okay, definition of congruent angles means that they have the same angle measure, which these would, but the statement is angle A is congruent to angle A. That is a reflexive property because it's restated the same angle. It looks like itself. So how I remember it is reflexive reminds me of reflection. And when I look in a mirror, I'm seeing myself back. So it's a reflection of myself. So it should be changed to the reflexive property of congruence. And then question 4, find an examples of similar triangles in the real world, submit links to the photos of them, and analyze the photos to write a paragraph proof of why the triangles have to be similar. Okay, so we have Google up. I would type in example of similar triangles in the real world. And I'm going to go to images and look for some real world ones. I want pictures of actual things, so no diagrams. So this one looks like it has the height of an Eiffel Tower. So I click on that, and the broomstick's height equals the length of its shadow. The height of the tower equals the length of the shadow. So how to do this, I would click on this. You can copy image address, come over here, I just pasted it, so I hit Control Ctrl-V, and then I can type. Okay, why are these photos, why are they similar? And they are because the information right here is height of the tower is equal to the length of the shadow. So it was a predefined notion, so that means that this length and this length are congruent, and this length of the broomstick is equal to its length of its own shadow. And we have corresponding parts, and then we have an angle. So we have a side angle side, side angle side. Congruence similarity theorem. And it's because if I took the height of this broomstick, I would have to multiply it, say, by 4 to get the height of the tower. Well, if the length of its shadows are the same, that means the length of the shadow would have to be multiplied by 4 in order to get this length of the shadow. And the ratio of corresponding sides would be the same. So the ratios of corresponding sides are the same, and we have the congruent angle because right angles are always congruent to itself. So I would write the scale factor from the broomstick length to the length of the height of the tower would be the same as the scale factor from the broomstick shadow length to the tower shadow length. So we have corresponding sides with the same ratios. With the same scale factor, which would result in the same ratio of corresponding sides. And since all right angles are congruent to each other, we would have side angle side similarity theorem for congruent similar triangles. So I would want the picture to be broken down and just a few sentences explaining which ones are corresponding sides, do they have the corresponding ratios for those sides, the same ratios for corresponding sides, and if they had the congruent, the same angle. Or you could use the angle-angle similarity theorem. So there's two different options for that. And I want you to, we're going to save and exit. And we'll pick up the next part in the next lesson.